Hey everyone, looking at section 11.4. So up until now, just to summarize, we've talked about just basic properties of vectors. We talked about three-dimensional space, what that looks like, how vectors act in three-dimensional space, and we talked about the cross product. So now, or the dot product. Yeah, getting ahead of myself again. Today we're going to talk about something called the cross product. So if you remember from last video, the dot product is a way that we can multiply two vectors together and get a scalar as the result. The cross product is a way that we can multiply two vectors together and get another vector as a result. Um, this little list here is kind of just a preview of what we're actually going to be using cross product for in this course. Um, but there are plenty of applications of the cross product. Before I get into any kind of heavy computation, just an idea of what the cross product kind of represents in space. So let's say that I have these two vectors, right? We're tail to tail, something like this. Got vectors A, oh, that's a cat, and B. So if I wanted to take the cross product, the resulting vector would have a magnitude that we can compute, right, using some of the stuff that we know about just vectors in general. All right, we'll get to that in a little bit. But the direction, one of the most important things is understanding the direction that the cross product is going to go. And if you've encountered this in physics before, they may have shown you something called the right-hand rule. Right, the right-hand rule, which basically you take your right hand, okay, and depending on which cross product you're doing, because cross products are not commutative, right? A cross B is not the same as B cross A, right? If I wanted to find A cross B, the direction, this is what happens when you have cats. Come on. Yep. All right, but anyway, A cross B. I would start moving my right hand in the direction that would push the vector A into the vector B. So A cross B, my thumb is gonna end up pointing up out of the page. So A cross B, up out of the page. All right, so essentially we're gonna end up with a vector that is pointing in this general direction. One thing I want you to notice about this vector is that it's perpendicular or orthogonal to both A and B, which is only possible in three dimensions or higher. Right? So cross product is not something we typically do with two dimensions because the result is going to end up in a third dimension. Right? And you can even think about it in terms of your three-dimensional coordinate system. Right? So like if we have the XY plane here, right? If I were to push the X into the Y, I would get Z, or the Y into the X, I would get Z, right? So in other words, the unit vector I cross the unit vector J results in the unit vector K. All right, and with that said, let's look at how we can calculate the cross product and how we can use it to do other stuff. Now, before we actually get into finding cross product, just a bit of a computational prerequisite. So you may have heard of matrices before. You can think of them as just a collection of vectors for the purposes of this course. And if you ever take a course in linear algebra, then you'll learn a lot more about them. Right? But when we talk about the dimensions of a matrix, m by n, m tells you how many rows go across, and n tells you how many columns go vertical, up and down. So if I have this 2 by 2 matrix, I can interpret it as a collection of two column vectors or two row vectors, right? Um, One of the things that we really need to understand about matrices is how to find the determinant of a matrix. It's not terribly important that you have a conceptual understanding of determinant at this point for this course. Again, that would be more of a linear algebra topic. But we do need to know how to find a determinant. So starting off simple, let's say we want to find the determinant of this 2 by 2 matrix. For 2 by 2s, all we have to do is crisscross applesauce. So we start by multiplying our diagonal elements. So -1 times 6 minus, right, and that minus is important, the other diagonal, the product of these two elements, 3 times 4. Okay, so this one minus this one. And when I combine these, I end up getting -18. So that is the determinant of that 2 by 2 matrix. Now, everyone, take a minute and pause the video. I want you to try to find the determinant of this matrix. All right. So for this one, first diagonal, we get 6 times 3 minus 2 times 1. That gives me 18 minus 2, or 16. So for a 2 by 2 matrix, it's pretty straightforward. It's just diagonal minus other diagonal. For a 3 by 3 matrix, though, it gets to be a little bit more involved, and the 3 by 3 is the one that we need to actually be able to do to find cross products and other things. So for 3 by 3 matrix, we're basically going to take this and break it down into a bunch of 2 by 2s. And here's how that works. Basically, I'm going to draw a line through the column and row, or first column, first row. All right. Where they intersect, that's going to be the coefficient for the first term. What's left over is a little 2 by 2 whose determinant I have to find. Okay, now I have to do this with every column in the first row. So we got the first column. Now if I look at first row, second column, where do the lines intersect? They intersect at 2. However, since this is an even column, like an even number column, it's the second column, we have to subtract. 2 is the coefficient because that's where the lines intersect. And then what's not crossed out forms that 2 by 2. So we have 0, 3, and 1, 0. And that's the second row. Now the column. The third column, our lines are intersecting at 4. This one we're adding. So we only subtract for every other column. So first is positive, second we subtract, third we add. If we had a fourth, we would subtract again. If we had a fifth, we would add, etc., etc. And then these 4 numbers that are left over are going to make that 2 by 2 matrix. And now all we have to do is find these determinants and a little bit of arithmetic. So for this one, 6 times 0 minus 1 times 2. Okay, for the second matrix, we get 0 times 0 minus 1 times 3. For the third matrix, 0 times 2 minus 6 times 3. And we do a little arithmetic. So 6 times 0 is 0. Minus 2, we get negative 2. All right, and then that'll become negative 3. And this will become negative 18. So now doing a little arithmetic, we get negative 2 minus negative 6, so plus 6 minus 72. That gives me negative 68. So that's the determinant of that 3 by 3 matrix. Okay, so how do we use these determinants to actually find the cross product? Well, if I want to find the cross product of two vectors, specifically three-dimensional vectors, we could do more, but no need. Essentially, we're going to write each of the vectors as a row in a 3 by 3 matrix. The order that you write them in is important because remember, cross products are not, or not cross products. Yeah, cross products are not commutative, right? So if I wanted to find, say, U cross V, I'll write that here. All right, I would put the elements of the vector U as the second row, elements of V as the third row. The first row is always going to be reserved for our unit vectors I, J, and K. And then, of course, using what we just learned about taking determinants, right? We can rewrite this using these 2 by 2 matrices. So let's say that we have these two vectors U and V. For the first one, we want to find U cross V. That's going to be the determinant of this 3 by 3 matrix. First row, we're going to have our unit vectors. Second row, we're going to have the coefficients, right? So you don't want to include the I, J, and K, just the coefficients of the vector U. So 1, negative 2, 1. And third row, we do the same for vector V, 3, 1, negative 2. Now, if we use the same ideas that we did last time, okay, Kitty, you want to teach? Anyway, so if we go through and do the same idea that we did last time, we'd start off with first row, first column. We would get I times the determinant of negative 2, 1, 1, 2, 1, negative 2. Yeah. For the second one, okay, come here. Silly. For the second one, right, we take out the second column. So we would end up with minus J times the determinant of this 2 by 2 matrix, 1, 3, 1, -2. And then for the third one, take out that third column, and we would end up with plus k times the determinant of 1, 3, -2, 1. Okay. So at this point, all we have to do is find these determinants for the 2 by 2s. And then the result is going to give us a vector. So for the first one, -2 times -2, we get 4 minus 1 gives me 3. So 3i. Second one, 1 times -2, we get -2. Subtract 3, we get -5j. And then for the last one, we have 1 minus -6. So 1 plus 6. That gives me 7k. And this vector represents the cross product of u cross v. So if you were to plot these vectors in three-dimensional space, let's say that we have the two vectors, we run a sheet of paper that contains both of them, and then we use our right-hand rule, right? Remember, we're putting u into v, so that would determine whether we're coming out this way or going in this way, right? Now, if I were to do the opposite, v cross u, we did say that cross products are not commutative, right? So if I switch the order, I will probably get a different answer. All right, because even the way we set up our matrix is going to be a little different. So here, for the last example we did, u was the second row and v was the third row. That's because u came first. Here, v comes first, so v needs to be the second row. So we get 3, 1, -2 as the second row. And then u is the third row, 1, -2, 1. And then we do the same thing. So if you cover up, the I column, we get I times the determinant of this matrix. If you cover up the second column, we end up getting minus j times the determinant of this matrix. And then if you cover up the third column, we end up getting k multiplied by the determinant of this matrix. And just like before, we just need to do the arithmetic to figure out these coefficients. So here we have 1 minus 4, so I get -3i. And then for this one, we get 3. Oh, whoops, correction. It should be a plus. Yeah, and then for this one, we get 3 minus -2. So 3 plus 2 is +5. But because of that minus, that'll become -5. And then for k, -6 minus 1, we get -7. And that's the vector that we get for v cross u. What do you notice? I notice that this vector is essentially this one, but with all of the signs flipped. It's actually a property, right? So anytime that we flip the order of a cross product, the result is just the negative of what we would have got. So this is really just the negative of U cross V. And it's a pretty neat property. And if you think about the right-hand rule, it says to use the right-hand rule to justify what you noticed, right? If you think about the right-hand rule, it just changes what direction I'm pushing, right? So if I did U cross V, I might go boom. But if I did V cross U, I might have to go boom. So I'd be pointing down at that point. So you notice if you start with one and then switch the order, right, your thumb will end up pointing in opposite directions because of that property. So anyway, last one, V cross 2V. Okay. So this is going to be the determinant of this matrix. Since V is the first one, we're going to write that as the second column. So it's 3, 1, -2. Now the third column is going to be double V. So all of these coefficients, I have to multiply them by 2. 3 times 2, I get 6. 1 times 2, I get 2. -2 times 2, I get -4. All right, now I've got my determinant set up, and we go just like before. So if I take out the I column, we get I multiplied by this determinant. Okay, and then if I take out the second column, we have minus J times this determinant. And then take out the third column, and we get K multiplied by this determinant. And let's see what happens. So for the first one, we get -4 minus -4. So -4 plus 4, that's 0. For the second one, 3 times -4, that's -12, minus -12, also 0. And then for the last one, 6 minus 6, still 0. So the result we got here is actually the 0 vector. Kind of strange. But let's think about something. In all of these cases, the second row is a multiple of the first row. So when I multiply, or so because I'm multiplying like this, I'm always going to end up having a number minus itself as that determinant. So as long as this second row is a multiple of the first row, the component for that direction is going to be 0. Meaning that if I take the cross product of a vector and any multiple of itself, I'm always going to get the 0 vector. It's another interesting property of cross products. Okay, some notes about the cross product. We've already kind of talked about them, but to summarize, the resulting vector is always orthogonal to both vectors. Remember, if I have two vectors on a piece of paper, the cross product will be poking out of the paper, which would be orthogonal or perpendicular to both of the vectors in the paper. We can use the right-hand rule to justify what we noticed about the first two cross products. Basically, if you switch the order of the cross product, you negate the answer. And then lastly, if you cross a vector with any multiple of itself, including 1 times itself, you end up getting the 0 vector, which corresponds to literally just a point. Okay, next example. Find a unit vector that is orthogonal to both u and v. So first thing we need to do is figure out a vector that's orthogonal to both u and v. Well, gee, what can I do to find a vector that's orthogonal to both of them? I can find their cross product. And it doesn't actually matter whether I do u cross v or v cross u, either one will result in a vector that is orthogonal to both u and v. That means that for this question, there actually are two possible answers, right? But I'm going to do u cross v. So we're going to start with u cross v. For that, we need the determinant. All right, since u is first, we're going to have the second row as these coefficients, 1, -4, 1. Since u is second, we'll have the coefficients for v. Did I say u? I meant v. In the third row. All right, so 2 is the coefficient for I, 3 is the coefficient for j. You might notice there's not a k there. That just means that the coefficient for k is 0. All right, and using our same thing, right? If I cover up the I end up getting I times the determinant of this guy minus j. If I cover up the j row, we get the determinant of 1, 2, 1, 0. Plus k, and if I cover up the k, I keep saying row, the k column, we get the determinant of this 2 by 2. So for the first component, we get 0 minus 3, so -3i. For the second determinant, we get 0 minus 2. Since there's already a negative there, that will become plus 2j. And then for the third determinant, 3 minus -8, so 3 plus 8, so 11k. So this is the cross product. This gives me a vector that is orthogonal to both u and v, right? The question, though, specifically asked me to find a unit vector that does that. So if I remember back from earlier in the course, if I want to find a unit vector in the direction of something, I need to multiply the components of something by the magnitude, so divide by the magnitude. I need to find the magnitude first. So magnitude, we get magnitude of u cross v, right, is equal to the square root of each component squared added together. So that's 9 and 4 make 13 plus 121 makes 134. So square root of 134 is the magnitude of u cross v. I'm not going to worry about simplifying that. If I want to write my unit vector out, remember that's going to be our cross product, u cross v, divided by the magnitude of the cross product, u cross v. So the result would be -3 over square root 134 I plus 2 over the square root of 134 j plus 11 over the square root of 134 k. That is our answer. Now, had you done this the other way and done v cross u instead, you would have got these same numbers, but the signs would have been switched, right? So if you did v cross u instead of u cross v, you would have got 3 over square root 134i minus 2 over square root 134j minus 11 over square root 134k. Yep. So if you did the other way and you got that, kudos. All right. So next, some applications of the cross product. Now that we are hopefully comfortable computing the cross product, what are some things we can use it for? So one application is that if I take the magnitude of a cross product, it actually gives me the area of a parallelogram that's formed by the vectors u and v. An alternative way of finding the magnitude of the cross product is using this formula. Notice it looks a lot like the dot product formula. The major difference is that we're using a sine instead of a cosine. And again, this only tells us the magnitude. It doesn't actually give us the cross product. But if we only want the magnitude, then this is a shortcut as long as we know the angle theta. If we don't, then we kind of just have to find the cross product and get the magnitude. So let's take a look at this next example. We've got vertices of a quadrilateral are listed below. Show that the quadrilateral is a parallelogram and find its area. So yep. So first thing, I want to write out each of the side lengths for this parallelogram. Yeah, as a vector. So for example, I could start off by finding vector AB. So here we're assuming A to be the initial point, B to be the final point. All right, shorthand component form. For the x component, final x, that's going to be 2 minus initial x, 5. So that gives me -3. Final negative 6 minus initial 2, I get 4. And then final 1 minus initial 0, I get 1. So one edge of the quadrilateral can be described by this vector. So next, let's say that I use BC as another side on my parallelogram. So here B is the initial, C is the final. So 2 minus 2, I get 0. 4 minus 6, I get -2. 7 minus 1, I get 6. Next, we're going to look at CD. So C is the initial, D is the final. So 5 minus 2, we get 3. 0 minus 4, we get -4. And 6 minus 7, we get -1. Lastly, we have DA. So here, D is our initial point, A is our final point. Think of it, we kind of just connected the points on the quadrilateral. We went A, B, C, D, back to A. So final minus initial, we get 5 minus 5, 0. 2 minus 0, 2. 0 minus 6, -6. Okay. So addressing the first part, we want to show that this quadrilateral is a parallelogram. What do you remember about parallelograms? One of the most fundamental properties of a parallelogram, the way it gets its name, is that pairs of sides are parallel to each other. So parallel vectors. Remember, how do I know if two vectors are parallel to each other? One is a scalar multiple of the other. So let's look at these 4 vectors that we just found. So look at the first one, AB. Is there any of these vectors that looks like it could be parallel to AB? Hopefully we said yes, CD. right? Notice if I multiply AB by -1, I get CD, which means that AB is parallel to CD. Okay. Now look at the remaining two vectors. Are these scalar multiples of each other? Yes. If I multiply BC by -1, I get DA. So in addition to AB parallel to CD, we get BC is parallel to DA. And if you had chosen to do this as AD instead, this would still track. So we've got these two facts combined tell me that opposite sides of the quadrilateral are parallel to each other. Since that's true, we know that the quadrilateral is a parallelogram. And for me to find, and for me to find the area of the parallelogram, I just need to find the cross product between two of the vectors. The thing is, this will only work if we take the cross product between two vectors that are adjacent to each other, meaning they're neighboring each other. And I want you to think back to your properties. What would happen if I did AB cross CD? Because remember that these two are scalar multiples. So if I take their cross product, I would end up just getting the zero vector, which isn't helpful to me at all. Right? But if I were to choose AB and either of these other two, I would get my answer. Or if I were to choose CD and either of these two, I would get the same answer. Right? So let's say that I choose AB cross BC. We know that's going to be the determinant of this matrix where components for AB go first. So -3, 4, 1. And then for BC, we get 0, -2, 6. So the result, we get I, if I cover up the I column, we get 4, -2, 1, 6 minus J. If I cover up the J column, we leave behind -3, 0, 1, 6. And if I cover up the K column, we leave behind -3, 0, 4, -2. So taking all of these determinants, we get 24 minus -2, so 26i. We get -18 minus 0, so -18, but since we're subtracting, that becomes plus 18j. And then 6 minus 0, we get plus 6k. Yeah. So to find the area of this parallelogram, we're going to find the magnitude of the cross product we just calculated. So that's going to be the square root of 26 squared plus 18 squared plus 6 squared. And sheesh, that's a big number. Yeah, I need my calculator for that one. By the way, remember you do get a scientific calculator on exams and quizzes for, that reason. Okay, so typing in. All right, this ends up giving me the square root of 1,036. Right, and that's not actually a perfect square, so I'm not gonna decimal that. And there we go. We found the area of that parallelogram. Look at us. All right. So another application, because as I mentioned, this course makes physics make sense because it teaches you all the stuff that you really need to know about vectors in a way that isn't just here, boom, go. All right. So what we're going to talk about next is the moment of a force about a point. When we say that, that's essentially like the tendency of an object to move along like a curved pattern, right? Like imagine I have a lever, yeah, and I'm pulling the lever down, right? So here we're rotating about the point of my elbow, right? And how easy or hard it is for me to move this lever about that point is the moment of that force. There's another word for that, torque. Yep. So torque, we can use cross products to compute the torque about a point. So let's say that we have a vertical force of 50 pounds applied to the end of a 1 foot lever that is attached to an axle at a point P. Find the moment of this force about the point P when theta is equal to 60 degrees. So basically we've got our point P. We've got this lever that is 1 foot long. And we know that the angle made with the horizontal is 60 degrees. Okay. So, a sec here. High quality H2O. So, getting back to this question, basically we have a lever. We know that the length of the lever is 1 foot. We know the angle is 60 degrees, and we know that there is a vertical force being applied to the lever, right? So, the moment of a force about a point, or the what's it called, torque, is defined as the cross product between this vector, right, and the force that's acting on that vector. So for this one specifically, if we call this point Q, the torque is equal to PQ cross F, right? So vector being acted on cross force that's acting on it. So we need to figure out a way to write both the component form of this and PQ. Lucky for us, I want you to real quick in your brain imagine a circle here. Unit circle. All right, if I wanted to write PQ in component form, do that down here. Remember, we can decompose this vector into its x and its y component, right? So think about it, if I go out 1 unit along this radius, right, at an angle of 60 degrees, the x coordinate is going to be cosine of that angle. So cosine of 60 degrees I, and the vertical component is going to be sine of that angle, right? Because that's our y coordinate. So plus sine of 60j. All right. So remembering our unit circle, we know that cosine of 60 degrees is 1/2, and sine of 60 degrees is the square root of 3 over 2. And here we don't have a k component, right? We're just considering this as a, well, really thin lever in a plane, which is also fine because guess what? The force is a completely vertical force, all right? So we know that the force is only going to be acting in the y direction. So for the force vector, we're actually going to, oh, whoops, yeah. So for the force vector, we're actually just going to be, we're only going to have one component that's non-zero. And a quick addendum here, y'all. Actually, you know what? It's fine. Frame of reference is fine. All right, so we're going to let the vector f, okay, be 0, yeah, 0, 0, -50. I do want to add that addendum though. So rather than considering this to be the y-axis, we're going to call it the z-axis, right? Because remember, if we have our three-dimensional graph, that's the z-axis, this is the x, and this is the y. So we don't have anything happening in the y direction. So I'm actually going to label this as k. There we go. K. Okay. So now that we've made that addendum to kind of fit this to a three-dimensional space rather than a two-dimensional one, right? Let's go ahead and find the cross product of these two vectors. So we know it's going to be a determinant. And we know we're listing PQ first. All right, so 1/2 for the I, 0 for the J, and square root of 3 over 2 for the K. And then 0, 0, -50 for the force F. So finding these determinants, if I cover up my I column, we get I times the determinant of this matrix. All right, if I cover up the J column, we get minus J times this determinant. And lastly, if I cover up the K column, we leave behind a half with a bunch of zeros. All right. So here's the thing. Whenever I have a row or a column that's all zeros, the determinant will end up being 0, right? To illustrate, 0 times that, we get 0, minus root 3 over 2 times 0, 0. 0 minus 0 gives me 0. So I don't have an I component. For this one, we get -25 minus 0. Since there's already a minus in front, this will become 25j. And then lastly, for k, that has a row that's 0. So I know the determinant is going to be 0. We get 0 minus 0. So there's no k component either. The torque is completely in the y direction, which is an interesting idea, right? If I add a force that causes a rotational motion, right, the resulting the resulting torque is going to be in a direction that's perpendicular to the plane of that motion, right? So if I'm doing a vertical force down, the torque is a force that's going out of the page. Pretty cool. So the torque would be this force 25J. If I wanted the magnitude of the torque, which might be what you would typically get in a physics class where they're focusing on like one-dimensional motion or even two, right? Then I would say that the magnitude of the torque is 25 pound feet. Ugh, that sounds painful. Anyway, so that is another physics application of the stuff that we're learning. Okay, now for this last little bit, we're going to look at something called the triple scalar product. And this is going to be particularly helpful to us because it allows us to figure out if three vectors are all in the same plane. So to preface that, if I were to draw any two vectors in three-dimensional space, I will always be able to slide a sheet of paper into those two vectors so that both of them are on that sheet of paper. However, if I were to draw a third vector, that one does not have to be in the same plane. It could be, but it might not be. So we can use this quantity called the triple scalar product to determine whether or not three vectors are in the same plane. If they are, what we'll notice is that this triple scalar product, which we have the formula for those here, would be zero. So for three coplanar vectors, the triple scalar product is zero. If our triple scalar product is non-zero, then the vectors are not in the same plane. But it does actually give us a quantity that is something that you typically are asked to find in a Calculus 3 class. Specifically, it gives you the volume of a parallelepiped with those three vectors making one of the corners. So you might be like, what in the world is this dude even saying? Is that even English? Yeah. So parallelepiped is basically like a rectangular prism or a box if it were slanted. So think of it as like a prism whose faces are all parallelograms. Right? So that would be an example of a parallelepiped. It's like I took a box and I just slanted it. And in this case, the three vectors might be something like this. So you see those three vectors are clearly not in the same plane. It would be impossible for me to stick a sheet of paper through all three of them. I could stick a sheet of paper through any pair of them, right? But not all three at the same time, which is why we would say that they're not coplanar. Um, another thing I want you to notice is that these three vectors are all tail to tail, which when we write our vectors in standard form, that's already the assumption, right? But you see how these three vectors make up a corner of our slanty box, parallelepiped. That's those are the three vectors whose triple scalar product we want to find the volume of the shape. All right. Another thing I want to point out here. When we take the determinant of this matrix, the result is going to be a scalar. The reason that cross products ended up being vectors is because here, or when we did cross products, our first row were all unit vectors. In this case, U1, U2, U3, they're all scalars. They're components of a vector, but each of them themselves is a scalar. So we know the determinant of this matrix would be a scalar value. It would represent the volume of a three-dimensional shape. Makes sense. This, let's analyze a little bit. Remember PEMDAS. If I look inside these parentheses first, what do I see? I see a cross product. If I take a cross product, what is the result? Is it a scalar or is it a vector? It's a vector. All right, so I have U, which is a vector, dot, like the dot product, this guy, which is another vector. And if I take the dot product of two vectors, what is the result? Hopefully we all emphatically said it's a scalar. So the triple scalar product is a scalar value. You should get a number for your answer for this one. All right, and again, here's what we're looking for. We want to know whether or not this triple scalar product is zero. If it's zero, the three vectors are all in the same plane. I could stick a sheet of paper through all three at the same time. If the result is non-zero, then we have this kind of case where the three vectors make the corner of a slanty box or a parallelepiped. And at that point, the scalar value we compute is the volume of that parallelepiped or slanty box, right? So let's look at one last example. So we want to determine whether these three vectors are coplanar. The way we do that is by looking at the triple scalar product. If they are not, determine the volume of the parallelepiped, having these three vectors as adjacent edges. Right, so basically find your triple scalar product. If it's zero, the answer is yes. If the answer is not zero, then the answer is no, and the volume of our slanty box is the answer we got. So one way we could set this up is by just listing the components of the vectors like this and finding a 3x3 determinant. That's the quickest, in my opinion, the easiest way to do it. You also could find the cross product V times or V cross W and then do the dot product of U with that cross product. But that sounds like a lot of work. I feel like it's easier to just set this determinant up and find the determinant since, that's equivalent to just finding a cross product. So I'm going to list the vectors out. The order isn't really all that important because if we were to switch rows in a matrix, that just changes the sign of the determinant. For that reason, we're never going to say that the volume is negative, right? We're always just going to take the absolute value of whatever we get for the triple scalar product. So I'm going to go in order, U first, V second. Oh, whoops. 0 for the I component, 2 for the J component, -2 for the K component, and then W last, 3, 1, 1. Okay. So remember how this works. It's just like if we were doing a cross product. Start off by covering up the first column. The top number was 3. The 2x2 determinant that's left over, remember we're taking out the first row for all of these. 2x2 that's left over, we get 2, 1, -2, 1. Okay, minus, and then we look at our second number, that's -5, minus the negative will be positive. And if I cover up first row, second column, we leave behind 0, 3, -2, 1. Then for the third column, cover up third column, first row, we get 0, 3, 2, 1. Okay. So now computing all of these little determinants, we get 2 minus negative 2, that's 4, plus 5 times 0 minus negative 6, so 5 times positive 6, plus 1 times 0 minus 6. And when I add these together, we get 12 plus 30 minus 6. That's going to be 36. Okay, so that is the triple scalar product, 36. Side note, this means that U, V, and W are not coplanar. The volume of the parallelepiped or the slanty box formed by those three vectors is equal to 36. And there we go. That's our answer. So now we know how to figure out if three vectors are coplanar, meaning can I stick a sheet through all three at the same time? We know how to find the volume of a parallelepiped. We know how to find the area of a parallelogram, which is one of the faces of a parallelepiped. We learned a little bit about torque and determinants. It's a good amount of work we did today. All right, y'all. That's all I got for cross products. That completes section 11.4. So go do your homework. Happy mathing.